Many problems in logistics can be formulated as integer programs. You may be thinking about formulating an integer program to figure out where Amazon should be opening the next fulfillment centers over the next 10 years to serve its customers in the most efficient manner. You may be thinking about formulating an integer program to decide how to match drivers to passengers over the next few minutes in an Uber type of ride-sharing system. Or you may be thinking about formulating an integer program to decide how to route the trucks, how to route the garbage trucks throughout the facility to do the garbage collection in the most efficient manner. So many problems in logistics can be formulated as integer programs. And in this lecture and the next one, we're going to look at a few problems in logistics, and we're going to see their integer programming formulations. And as we formulate these problems in logistics as integer programs, we're also going to see new interesting modeling tricks. So the first problem that we're going to look at today is called the facility location problem. Here's what the facility location problem looks like. Okay. So we're going to talk about the facility location problem. In the facility location problem, we have a whole bunch of locations that can serve as potential facility locations. So let's say these crosses are potential facility locations. So we can open facilities at these potential facility locations. Let me put one more of those. Okay. And also we have a whole bunch of demand points. So these red circles are demand points. So you can think of demand points as cities. So we're going to open facilities at some of these potential facility locations. There's a cost of opening a facility in each one of these potential facility locations. And then once we open our facilities, we're going to connect the demand points to a facility location. We're going to connect the demand points to an open facility location. And there's a cost of connecting a demand point to a facility location. And we want to figure out where to open our facilities and which demand points to connect to which facility locations, which open facility locations, so that we minimize the total cost of opening the facilities and connecting the demand points to the facility locations, while also making sure that each demand point is connected to one facility location. Okay, so this is the facility location problem. We have a whole bunch of potential facility locations, and we have a whole bunch of demand points. We can think about these demand points as cities. We're going to open facilities at some of these potential facility locations. There's a cost of opening a facility in each one of these potential facility locations. And once we open our facilities, we're going to connect the demand points to the open facility locations, and there's a cost for connecting a demand point to a certain facility location. And our goal is to figure out where to open the facilities and which demand points to connect to which open facilities, such that we minimize the total cost of opening the facilities and connecting the demand points to the facility locations, while making sure that each demand point is connected to exactly one facility location. Okay, so this is the facility location problem. Let's lay out the location for the facility location problem. We're going to let F be the set of potential facility locations. We're going to D be the set of demand points. Let's let Fj be the little fj be the cost of opening a facility at potential facility location J. Cost of opening a facility at potential facility location J. And let's also let C sub ij be the cost of connecting demand point I to a facility in facility location J. Cost of connecting demand point I to facility location J. So this is our data. F is the set of potential facility locations. D is the set of demand points. Fg is the cost of opening a facility at potential facility location J, and Cig is the cost of connecting demand point I to a facility location J. So for example, the solution to the facility location problem could look like this. We open facilities at these 3 locations, and then we connect these demand points to this facility location, and then we connect these demand points to this facility location, and then we connect these 2 demand points to this facility location. So this is what the solution to a facility location problem could look like. Okay, good. So now let's formulate the facility location problem as an integer program. Again, F is the set of potential facility locations, D is the set of demand points, Fj is the fixed cost of opening a facility at facility location J, and then Cig is the cost of connecting demand point I to a facility location J. Great. Then to use our decision variables, for our decision variables, we're going to have 2 sets of decision variables. So let's let xj be a binary decision variable. Xj takes value 1 if we open facility at potential facility location J. Otherwise, xj takes value 0. So xj's are telling me which facility location will be open. And let's define another binary variable. Let's define another binary decision variable. Let's call it as y sub ij. And y sub ij takes value 1 if we connect demand point I to facility location J. The decision variable y sub ij takes value 1 if we connect demand point I to facility location J. Otherwise, y sub ij takes value 0. Great. So those are our decision variables. Now we need to write some constraints that capture the logical relationship between the x and the y decision variables. Namely, if we do not have a facility open at facility location J, then we cannot connect demand point I to facility location J. Let's say it again. There's a logical relationship between the x and y decision variables, which is that if we do not have a facility open at facility location J, then we cannot connect demand point I to a facility location J. So written in math notation, if xj is equal to 0, if we do not open a facility in facility location J, then yij has to be 0, meaning that we cannot connect demand point I to a facility in facility location J. On the other hand, if you open a facility in facility location J, if xj is equal to 1, then we can connect, or we may not connect, the demand point I to facility location J, so yij can be both 1 or 0. Okay. We need to write constraints to capture this kind of a logical relationship. And we're going to capture this logical relationship by using a constraint that looks like this. Yij is less than or equal to xj, meaning that if xj is equal to 0, if the right-hand side of this constraint is 0, then this is going to push the yij variable to be equal to 0 as well. If you don't open a facility at facility location J, then we're not going to be able to connect demand point I to facility location J. If xj is equal to 0, this constraint is going to push yij to 0. If on the other hand xj is equal to 1, if we open a facility at facility location J, then yij is going to be less than or equal to 1, so we will or we will not, however we wish, connect demand point I to facility location J or not. Good. If you open a facility at facility location J, if xj is equal to 1, yij is less than or equal to 1, so we're free to connect demand point I to facility location J. We may or may not do that connection though. Now we can write our integer program. We're going to minimize the total cost of opening the facilities and the cost of making the connections. Let's look at our all facility locations. xj takes value 1 if you open a facility at facility location J. And if you open a facility at facility location J, we're going to incur the cost of opening the facility, that is fj. So that is the total cost of the facilities that we open. To compute the cost of the connections, let's loop over all demand points. Let's loop over all facility locations. Yij takes value 1 if you connect demand point I to facility location J. If you connect demand point I to facility location J, we incur the connection cost of the demand point I to facility location J, and that connection cost is Cij. Okay, so in the objective function, we have the cost of the facilities that we open and the cost of the connections that we make. And as far as the constraints go, the first constraint we're going to write is going to look like this, which is saying that if facility location J is closed, then demand point I cannot be connected to facility location J. We have these constraints for every demand points and for every facility locations. And lastly, we need to write a constraint that ensures that each demand point is connected to one facility location. Each demand point is connected to one facility location. And we can write this constraint as follows. Yij takes value 1 if demand point I is connected to facility location J. Yij takes value 1 if demand point I is connected to facility location J. At overall facility locations, this is the total number of facility locations that demand point I is connected to. This is the total number of facility locations that demand point I is connected to. If we set that equal to 1, this means that the total number of facility locations that demand point I is connected to has to be equal to 1. Demand point I has to be connected to exactly one facility location. We have this constraint for every demand point I. Each demand point I should be connected to exact one facility location. And our xj decision variables are binary. And our yij decision variables are binary. Good. So this is the integer programming formulation of the facility location problem. We solve this integer program. The optimal values of the x variables are telling us where do we open our facilities, and the optimal values of the yij decision variables are telling us which demand points are being connected to which facility locations. Great. And in last lecture, we solved the branch and bound method to solve integer programs. But in practice, when we solve these kinds of integer programs, we do not need to program the branch and bound method. Fortunately, Groby has all the internal structure for us to formulate an integer program and directly solve an integer program. When we add a decision variable into our model, we had this in Groby, we had this add var subroutine. When we're adding a decision variable to our optimization model, in Groby we had the add var subroutine. And when we're adding a decision variable to our optimization problem, we specify the type of the decision variable. And so far, we specify the type of decision variable as a continuous decision variable in Groby. So when we're writing a decision variable to our model in Groby, we specify the type of decision variable. And so far, in all the work that we did, we specify the type of decision variable as a continuous decision variable. But when we're writing a decision variable to an optimization model in Groby, instead of using this type of the variable as continuous, we could use groby.integer. In this case, we ensure that the decision variable is going to take integer values in an optimal solution. Also, we could specify the type of decision variables as grb.binary. In this case, Groby ensures that when it's solving the optimization problem, Groby ensures that the decision variable that we added to the model is going to take binary values, 0 or 1. And of course, when we say optimizing Groby, in the background, Groby runs branch and bound, but we don't have to program this branch and bound on our own. Once we specify the type of decision variable as integer or binary, Groby is going to take care of all the branch and bound stuff in the background for us. Okay. This is the facility location problem. One of the, let's say, the shortcomings of this facility location problem is that when we get the optimal solution to this facility location problem, it may be that many of the demand points are connected to one facility, and you may not like that. We may not like that. We may say that, well, each one of these facilities can only serve a certain amount of demand, so it's not a desirable thing to see many of the demand points being connected to one facility location. There's another variant of the facility location problem called the capacitated facility location problem. In that variant, we try to figure out which demand point to connect it to which facility locations, but with the understanding that each facility location has a certain amount of capacity, and a certain amount of the total amount of demand that a certain facility location serves cannot exceed its capacity. Okay, so let's go ahead now and formulate the capacitated version of the facility location problem. Once again, in the capacitated version of the facility location problem, there is going to be a certain amount of capacity in each facility location, and the total demand that a certain facility location serves cannot exceed its capacity. So let's see what the capacitated facility location problem looks like. Capacitated facility location problem. Let's first write down the notation. Let's first write down the data. That doesn't change. F is still the set of potential facility locations. D is still the set of demand points. Fj is the cost of opening a facility at potential facility location J. And Cij is the cost of connecting demand point I to facility location J. So far, this is the old notation that we defined. So now let's think about our new notation. Our new piece of notation, one piece of our new notation is going to be D sub I. And this D sub I is going to be the demand at demand point I. And whenever we connect demand point I to a certain facility, the demand that we're going to impose on that facility is going to be whenever we connect demand point I to a certain facility, the demand that we're going to impose on that facility is going to be DI. Another new piece of notation is going to be, let's say, U is the capacity. Okay. Facility location. So whenever we connect demand point I to a facility location, we're going to impose a demand of DI to that facility location and use the capacity of the facility location. So the total demand that we impose, on a certain facility location is not going to exceed the capacity of a facility location. Okay, so that is the capacitated facility location problem. Same setup as before. Set of potential facility locations, set of demand points. Fg is the cost of opening a facility at potential facility location J. Cig is the cost of connecting demand point I to facility location J. But now each demand point I has a demand of Di, and each facility has a capacity of U units. And in the facility location problem, you want to ensure that the total demand that we impose at a certain facility location is going to be no more than the capacity of that facility location. Okay, so we're going to work with the same type of decision variables. Xg is going to take value 1 if we open a facility at facility location J, otherwise Xg is going to take value 0. And as before, while the binary decision variable Yig is going to take value 1 if we connect demand point I to facility location J. Yij takes value 1 if we connect demand point I to facility location J. Otherwise, Yij takes value 0. Good. So now let's think about writing a constraint that ensures that the total demand imposed on a facility location by all the demand points connected to that facility location is going to be no larger than the capacity of that facility location. Let me say it again. So now let's try to concoct a constraint that's going to ensure that the total demand imposed at a facility location by all the demand points connected to that facility location cannot exceed the capacity of that facility location. So let's write a constraint that looks like that. That ensures that. Okay, so here's how we're going to do that. Yij takes value 1. Yij takes value 1 if demand point I is connected to facility location J. Yij takes value 1 if demand point I is connected to facility location J. And if demand point I is connected to facility location J, we're going to impose a load of Di on facility location J. Okay? Let's say it again, Yij takes value 1 if demand point I is connected to facility location J. And if demand point I is connected to facility location J, demand point I is going to impose a load of Di on facility location J. So now let's add over all demand points. This sum that we're seeing is now the total load, the total demand imposed on facility location J by all demand points. Total demand imposed on facility location J by all demand points. Good. Which means that we're going to write a constraint that says, if facility location J is not open, then the total demand imposed on facility location J by all demand points has to be 0. And if facility location J is open, then the total demand imposed on facility location J by all demand points has to be at most U. Okay. We need to write a constraint that says that. Let's say it again. We need to write a constraint that says, if facility location J is not open, then the total demand imposed on facility location J by all demand points has to be 0. And if facility location J is open, then the total demand imposed on facility location J by all demand points has to be at most U. Let's write a constraint that says that. So we want to write a constraint that says the following. If xj is equal to 0, if facility location J is not open, then the total demand imposed on facility location J by all demand points has to be 0. Then the total demand imposed on facility location J by all demand points has to be equal to 0. But if the facility location J is open, then the total demand imposed on facility location J by all demand points has to be at most U. We need to write a constraint that satisfies this logical relationship. To capture this kind of logical relationship, here's the constraint we're going to write. Sum over I, di times Yij, is less than or equal to U times xj. So if you look at this constraint, if xj is equal to 0, the right-hand side of this constraint is 0. This is going to ensure that if xj is equal to 0, facility location J is not open. The right-hand side of this constraint is 0. That's going to ensure that the total load imposed on facility location J is going to be 0. On the other hand, if xj is equal to 1, the right-hand side is going to be U. Then this constraint is going to ensure that the total load imposed on facility location J is going to be at most U. Okay, this is the constraint that we need. So then we can put our optimization model together. Minimize the total cost of opening the facilities and connecting the demand points to the facility locations, while making sure that if facility location J is not open, then the total load imposed on facility location J has to be 0. Otherwise, the total load imposed on facility location J has to be at most U. Up, EI times Yij added up. And overall demand points is less than or equal to U times xj. We have this constraint for every facility location J. For every facility location J, if the facility location J is not open, the load imposed on facility location J has to be 0. And also, we also need to write a constraint that says the total number of facilities that demand point I is connected is equal to 1. So for every demand point I, the total number of facilities that demand point I is connected has to be equal to 1. So this ensures that each demand point is connected to a facility. And our xj decision variables are binaries for every facility location J. And our Yij decision variables are binaries for every demand point and facility location pair. Okay. If you solve this problem again, now we're going to find which facilities to open and which demand points to connect to which facilities, while making sure that the total demand that we impose on any open facility location doesn't exceed the capacities of the facility locations. Great. And this problem is called the capacitated facility location problem. If we compare our formulations for the capacitated and an uncapacitated facility location problem, in the capacitated facility location problem, we had a constraint that says if facility location J is closed, then the total load imposed on that facility location J is going to be 0. In the uncapacitated problem, we had this constraint that says if facility location J is closed, then we cannot connect any demand point I to facility location J. So we do not write these types of constraints in the capacitated facility location problem. And if we solve this version of the capacitated facility location problem, it's going to solve the problem just fine. But in general, it may not be a bad idea to add some additional constraints into the formulation of the capacitated facility location problem. So if we also add these constraints into the capacitated facility location problem, our formulation is still going to work. So we also added the constraints that says if facility location J is closed, you cannot connect demand point I to facility location J. And sometimes adding these extra constraints in your integer programming formulation of a problem is useful because even without these constraints, this formulation is going to find the optimal solution to the capacitated facility location problem. But if we add these constraints, then when we solve these linear programs at different nodes of our branch and bound tree, we may be more susceptible to finding integer solutions more quickly. So adding these extra constraints that seem to be redundant in the integer programming formulation may make the linear programs that we solve at each node of the branch and bound tree a lot tighter, may help us to get to an integer solution more quicker. So every now and then think about adding these extra constraints in the integer programming formulation, again, with the understanding that this makes the linear programs that we solve at different nodes of the branch and bound tree more likely to find an integer solution more quickly. Okay, good. Once again, from the integer programming perspective, these red constraints are redundant in the formulation of the capacitated facility location problem, but adding them up may make the branch and bound algorithm faster. Okay, these are two variants of the facility location problem, uncapacitated, capacitated, and there are a bazillion different variants of the facility location problems. People have looked at under different scenarios, different capacity constraints, and so on and so forth. But once you understand these two formulations, you can come up with all kinds of other variants of the facility location problem as well. So now, let's move to the next problem that we're going to look at. The next problem we're going to look at is called the dynamic driver assignment problem. Dynamic driver assignment problem. Here's how the dynamic driver assignment problem works. We have a bunch of locations in a geographical region, and we have a planning horizon. We're looking at a problem over a certain number. We have a planning horizon over a certain number of days. So we're looking at a problem over a certain number of days. So let's say we're looking at the problem over the next 2 weeks, over the next 14 days. Okay, so we have a bunch of locations spread around the geographical region, and we have a planning horizon that includes 14 days. At the beginning of the planning horizon, at the beginning of day 1, we have a whole bunch of drivers at these different locations. We know where our drivers are at the beginning of day 1, at the beginning of the selling horizon. And over the different days, on different days in the selling horizon, we have loads that need to be carried from different origins to different destinations. Like, for example, tomorrow we have 3 loads that need to be moved from New York State to Pennsylvania. We have maybe 4 more loads that needs to be carried from Maryland to Ohio on day 5. We have 6 loads that needs to be carried from Illinois to Indiana on day 8, and so on and so forth. Okay, let's say it again. We have a whole bunch of locations spread around the geographical region. We're looking at the problem over a planning horizon composed of a whole bunch of days. So let's say we're looking at the problem over the next 14 days. At the beginning of the selling horizon, at the beginning of day 1, we have our drivers located at certain locations in our transportation network. And over the course of the planning horizon, over the course of the next 14 days, we have some loads that needs to be carried from different origins to different destinations in different days. In day 3, we have 3 loads that needs to be carried from New York to Ohio. In day 5, we have 2 loads that needs to be carried from Chicago to Iowa. In day 6, we have 4 units of 4 loads that needs to be carried from Kansas to Kentucky. You get the idea. When we carry a certain load, we're going to collect a certain profit. And our drivers can also sit idle at the current location that they're in without carrying any loads whatsoever. And let's assume that the travel times between every origin destination pair is 1 day. So that means that if a driver goes from location I to J on day T, he is going to be available in location J at the beginning of day T plus 1. And let's also assume that each driver can carry 1 load at a time. And we want to figure out during the course of the selling horizon which of these loads that we should be serving so that the total expected profit that we collect from the served loads is going to be as large as possible. So this is the dynamic driver assignment problem. Okay, quick recap, bunch of locations. We're looking at the problem over a selling horizon, let's say composed of 14 days. At the beginning of the selling horizon, at the beginning of day 1, we have our drivers located at different locations in our transportation network. And during the course of the selling horizon, during the course of the next 14 days, we have loads that needs to be carried from different origins to different destinations on different days. That's a part of the problem data. Let's assume that the travel times between those different locations is always 1 day. So if I go from location I to J on day T, my driver becomes available at location J at the beginning of day T plus 1. Let's also assume that each driver can carry 1 load at a time. And also driver can sit idle at the current locations that they're sitting at. And the question that we're interested in, over the next 14 days, which one of these loads we should be carrying so that we maximize the total profit that we collect from the loads that we carry. And the interesting twist of this problem is, the load carrying decisions that we make for the different days interact with each other. What I mean by that is, if a driver carries a load from location I to J on day T, then that driver is going to be available at location J at the beginning of day T plus 1. Okay, so this is the interesting twist of the problem. The load carrying decisions that we make on different days are connected with each other, meaning that if a driver carries a load from location I to J on day T, then that driver is going to be available at location J at the beginning of day T plus 1. Good. Let's write down the data for this problem. The data for this problem is, let's say N is the set of locations in the transportation network. Let's say T is the number of days in the planning horizon. Let's say SI is the number of drivers available in location I at the beginning of the planning horizon. SI is the number of drivers available at location I at the beginning of the planning horizon. SI is the number of drivers available at location I at the beginning of day 1. Part of the problem data. At the beginning of day 1, I know how many drivers I have at each location. SI is the number of drivers available at location I at the beginning of day 1. At the beginning of day 1, I know where my drivers are. Let's say Rij, R sub ij is the profit from carrying a load from location I to J. And lastly, let's say D sub ijt is the number of loads that needs to be carried from location I to J on day T. Number of loads available to be carried from location I to J on day T. So these are the data for our problem. And it's a set of locations in our transportation network. T is the number of days in the planning horizon. T is the number of days in the planning horizon. SI is the supply of drivers at location I at the beginning of the planning horizon. SI is the supply of drivers at location I at the beginning of day 1. RAG is the profit from carrying a load from location I to J. And DIG is the number of loads available to be carried from location I to J on day T. So this is our data. Let's think about our decision variables. One decision variable we're going to need, let's denote it by xjt. This is going to be the number of drivers carrying a load from location I to j on day t. xijt, our decision variable, one decision variable is xijt. That is number of drivers carrying a load from location I to j on day t. Okay, so decision variable xijt is the number of drivers carrying a load from location I to j on day t. Another decision variable, again, we said the drivers can sit idle, doing nothing at a particular location on a particular day. Let's say zit is the number of drivers sitting idle at location I on day t. xijt is the number of drivers carrying a load from location I to j on day t. If a driver is carrying a load from I to j on day t, then it's going to be available at location j at the beginning of day t plus 1. Zit is the number of drivers sitting idle at location on day t. If the driver is sitting idle at location I on day t, then it's going to be available at location I at the beginning of day t plus 1. He said idle at location I on day t, so he's going to be available at location I at the beginning of day t plus 1. Good. Let's try to get a feel for the types of constraints that we need to write. Let's try to get a feel for the types of constraints that we need to write. Let's think about what's happening in the first day. Let's think about what's happening in the first day. At the beginning of day one, I have SI drivers available at location I. At the beginning of day one, I have SI drivers available at location I. And those drivers are either going to carry loads out of location I, or they're going to sit idle at location I. Okay, let's see it again. At the beginning of day one, at the beginning of the planning horizon, we have SI drivers available at location I, and those drivers are either going to carry loads moving out of location I on day one, or they're going to sit idle at location I. Then one constraint we're going to write is going to look something like this. On day one, Xij1 is the number of drivers carrying a load from location I to j on day one. Xij1 is the number of drivers carrying a load from location I to j on day one. And over all locations, these are the total number of drivers carrying a load from location I to j on day one, added over all locations j. So this is the total number of drivers carrying a load out of location I on day one. This is the total number of drivers carrying a load out of location I on day one. Plus, these are the number of drivers, Zi1, these are the number of drivers sitting idle at location I on day one. So this is the total number of drivers carrying a load out of location I on day one, plus the number of drivers sitting idle in location I on day one. That should be equal to the number of drivers available at location I at the beginning of day one. Okay, so this is one type of constraint that we need. Let's say it again. Xij1 is the number of drivers carrying a load from location I to j on day one. Add overall j, this is the total number of drivers carrying a load out of location I on day one. And this is the number of drivers sitting idle in location I day one. So this constraint is saying the total number of drivers carrying a load out of location I on day one or sitting idle in location I on day one should be equal to the available drivers, number of available drivers at the beginning of day one. Okay, so this is what's happening in day one. Now let's think about what's happening in an intermediate day. Let's take an intermediate day. Let's take an intermediate day T. Let's take an intermediate day T, and let's look at location I on an intermediate day T. Let's look at location I on an intermediate day T. Day T. Good. Let's look at a location I on an intermediate day T. Well, drivers in location I can carry a load from location I to j on day T, and that's captured by the decision variable xijt. Drivers in location I can carry a load from location I to k on day T, and that's captured by the decision variable xikt. And the drivers in location I can carry a load from location I to L on dt, and that's captured by the decision variable xilt. So these are all the drivers that are carrying a load out of location I on dt. And also we have drivers sitting idle in location I on dt, and that is given by those drivers are given by the decision variable zit. So then all of this sum is the total now, all of these decision variables is giving me the total number of drivers carrying a load out of location I on dt, plus the number of drivers sitting idle in location I dt. So then this total, this sum, is going to be equal to the vehicle available driver supply available at location I on dt. Okay, let's write this down. xijt, xikt, xalt, add it all up, is going to be the total number of drivers carrying a load out of location I on dt. So then xijt added over all j is going to be the total number of drivers carrying a load out of location I on dt, plus zit. These are the total number of drivers sitting idle in location I on dt. So this sum that we're seeing here is the total number of drivers either carrying a load out of location I on dt or sitting idle in location I dt. And this should be equal to the driver supply in location I at the beginning of dt. And what is giving me the driver supply in location I at the beginning of dt? What is giving me the driver supply in location I at the beginning of dt? Well, I may have drivers that are moving from location j to I on dt minus 1. I have drivers who are who are carrying a load from location j to I on dt per t minus 1. And those guys are going to be available at location I at the beginning of dt. Likewise, I have drivers who are moving location k to I, getting a load from location k to I on day t minus 1, and they're going to be available in location I at the beginning of day t. And likewise, I have drivers who are getting a load from location L to I on day t minus 1, x L I t minus 1. These are the drivers who are carrying a load from location L to I on day t minus 1. They are going to be available in location I at the beginning of day t. And lastly, I have drivers who are sitting idle in location I on day t minus 1. They're going to be available at the beginning of location I, at location I at the beginning of day t. So then we said the total number of drivers moving out of location I on day t plus the number of drivers sitting idle at location I on day t should be equal to the driver supply at location I on day t. And the driver supply in location I day t is given by the number of drivers driving into location I on the previous day plus the number of drivers set idle in location I on the previous day. So then the number of drivers driving into location I on the previous days, xjit minus 1, xkit minus 1, xlit minus 1, all added all up. So that is given by xjit minus 1 added over all j. So these are the xkjit minus 1, xkit minus 1, xlit minus 1, all added up. And we also have the zit minus 1. Okay. So then this constraint that we wrote over here is saying the following. On the left-hand side, we have the total number of drivers carrying a load out of location I on dt plus the number of drivers sitting idle in location I on dt. So the total number of drivers carrying a load out of location I on dt plus sitting idle in location I on dt should be equal to the driver supply on location I at the beginning of dt. And the driver supply in location I at the beginning of dt is given by the total number of drivers driving into location I on the previous day plus number of drivers set idle in location I on the previous day. So that's the constraint that is going to ensure that whoever goes out of location I and sits idle in location I on day t should be equal to whoever came into location I and set idle in location I on the previous day. With that, we're ready to put our formulation together. We're trying to maximize the revenue that we make from all the loads that we carry over the whole selling horizon. We're trying to maximize the revenue. We're trying to maximize the profit from all the loads that we carry over the whole planning horizon. Right? There are capital T days in the planning horizon. And let's look at the all origin destination pairs. RIG is the profit from carrying a load from location I to J. And XIJT is the number of drivers who are carrying a load from location I to J on day T. So this is the total profit, overall origin destination pairs, and overall days throughout the whole planning horizon, which is what we're trying to maximize. Let's write our constraints. The first constraint we're going to write is going to relate to the initial supply of our drivers. The total number of drivers driving a load out of location I on day one, plus the number of drivers sitting idle in location I on day one, should be equal to the initial supply of the drivers at the beginning of day one at location I. The total number of drivers driving a load out of location I on day one, plus the number of drivers sitting idle in location I on day one, should be equal to the initial supply of the drivers available at location I at the beginning of day one. And we have these constraints for every location in our transportation network. Great. Now we have this other type of constraint, if you like. We have this other type of constraint that says the total number of drivers moving loaded out of location I on day T, plus the guys who sit idle in location on day T, should be equal to the total number of drivers moving loaded into location I on the previous day, and the number of people who sat idle in location I on the previous day. The number of drivers who's moving out of location I on day T and sitting idle in location I on day T should be equal to number of drivers moving into location I on the previous day and who sat idle in location I on the previous day. Let's write these constraints. XIJT at overall J plus ZIT is equal to xji t minus 1 at overall j plus zi t minus 1. And we have this constraint again for every location in our transportation network and for every day, 2, 3, all the way to the end of the planning horizon. Okay. Why do I not have this constraint for day one? For day one, the constraint I write is for day one, the drivers who drive out of location on I on day one, and the drivers who sit idle in location on day one should be equal to the initial supply at location I at the beginning of day one. So for day one, I don't need this to write this constraint. So the balance is satisfied by this constraint for day one. Okay, what other constraint do we need? We don't have infinite number of days on every day, so we need to write a constraint that says the total number of drivers that go from location I to J on day T, the total number of drivers who carry a load from location I to J on day T should be less than the number of loads available to be carried from location I to J on day T. So this was the number of loads available to be carried from location I to J on day T. So the number of drivers that carry a load from location I to J on day T is less than the number of loads available to be carried from location I to J on day T. This is a part of our problem data. We have this constraint for every origin destination pair and for every day in our selling horizon. And lastly, our decision variables XIJTs are integers. And ZITs are also integers. Good. So now we learned another modeling trick. And the important modeling trick that we learned over here is that we modeled a problem where the loads that I carry on day T minus 1 have an implication on where my drivers are going to be at the beginning of day T, which in turn will have an implication on what loads I can carry on day T. Okay, so the decisions that we make, the load carrying decisions that we make to each on different days are connected to each other. The loads that I carry on day T minus 1 dictates where my drivers are going to be at the beginning of day T, and where my drivers are at the beginning of day T have implications on which loads we can carry on day T. Okay. Good. So the load carrying decisions that we make on different days are connected with each other, and we ensure that connection through these types of constraints. Good. So as we wrap up this formulation, it turns out we can view this formulation as a mean cost network flow problem that takes place on a special kind of network. And let's see how we can view this problem formulation as a mean cost network flow problem that takes place over on a special kind of network. Here's a network we're going to draw. Let's consider the case where we have 4 days in the selling horizon and 3 locations, A, B, C, in our transportation network, just so that we can draw these things on a piece of paper. So let's look at the case where we have 4 days in the planning horizon, 4 days in the planning horizon, and we have 3 locations in our transportation network. So here's what we're going to do. Here is location A, B, C on day 1. So we're going to keep on replicating locations on different days. Here's locations A, B, C on day 1. Here's locations A, B, C on day 2. Here's locations A, B, C on day 3. And here are locations A, B, C on day 4. Okay. At the beginning of day 1, I have SA drivers in location A, SB drivers in location B, SC drivers in location C. At the beginning of day 1, I have SA drivers in location A, SB drivers in location B, and SC drivers in location C. Okay? So in this network then, let's put a supply of SA to this node. Let's put a supply of SB to this node. Let's put a supply of SC to this node. Okay. On day 1, I can go from location A to A. I can go from location A to B. And if I go from location A to B on day 1, I'm going to be in location B on day 2. I can go from location A to C on day 1. If I go from location A to C on day 1, I'm going to be in location C at the beginning of day 2. Likewise, I can go from location B to A, I can go from location B to B, I can go from location B to C. Let's keep going. I can go from location C to A on day 1, C to B, C to C. So these are the loaded movements that we do on day 1 between different locations. So these are the drivers who are carrying a load from location A to A on day 1. These are drivers who are carrying a load from location A to B on day 1. These are drivers who are carrying a load from A to C on day 1. These are drivers who are carrying a load from location B to C on day 1. These are drivers who are carrying a load from location C to B on day 1. These are drivers who are carrying a load from location C to A on day 1. You get the idea. Here we go with the understanding that we can carry a load from location A to A. For example, if you interpret these locations as states, New York, Pennsylvania, Connecticut. So there are loads that go from New York State to New York State, right? So that's allowed. So there are within state loads. So it's okay to carry loads from a certain location to another. So if you interpret these locations as states, there are loads that go from one state to the same state. Good. What else? What other movements do I have in this network? So for example, I can have a driver who was at location C on day 1 and set idle in location C on that day. So that driver is going to be available at location C on day 2. So these are ZC2 guys. Those are the drivers who set idle in location C on day 1, ZC1. ZC1. Likewise, I have these drivers who set idle in location A on day 1. And I have these drivers who set idle at location B on day 1. If my driver is sitting idle in location B on day 1, then he's available in location B at the beginning of day 2. Okay, so now let's replicate these kinds of arcs for the other days in our planning horizon. In day 2, I can go from A to B. In day 2, I can go from A to A to B, A to C. In day 2, I can go from B to A, B to B, or B to C. Or in day 2, I can go from C to A, C to B, and C to C. Those are loaded moments again. Now, for example, again, the flow on this car is corresponding decision variable, moments from A to B on day 2, XA, B2. The flow on this arc would correspond to the decision variable, moments from X, B to C on day 2. The flow on this arc would correspond to decision variable, X, C to C on day 2. And likewise, on day 2, I can set idle in each node. So I can sit at location A on day 2. I can sit idle in location B on day 2. And I can sit idle in location C on day 2. Let's put our moments for day 3. So these are the moments from A to A on day 3, C to B on day 3, E to A on day 3. You get the idea. You can also sit idle on day 3. Good. And how are we going to deal with the moments on our last day? When I make a moment on the last day, I don't care where my driver ends up. When I make a moment on the last day, when I make a moment on the 4th day, which is the last day in my planning horizon, when I make a moment on the last day in my planning horizon, I don't care where my drivers end up. I don't care which location they end up in, because I'm not making any decisions on day 5, right? So then to deal with that kind of a situation, here's what we're going to do. We're going to put one big node at the end. And people usually call this one big node as the sync node. And we're going to put a demand of SA plus SB plus SC on this big sync node. So let's put a demand of SA plus SB plus SC on this sync node, okay? So this node at the very end is a demand node. This sync node is a demand node, and the total demand at this node is equal to the total supply in our network. So then, if a driver goes from A to A on day 4, good, but I'm gonna let you go into the, I'm not gonna let you go into the sync node, because I don't care where you end up, because I don't have any decisions to make on day 5. So those are drivers going from location A to A on day 4. The driver goes from location A to B on day 4. I'm also going to let him go into the sync node, because again, I don't care where he ends up on day 4 at the end of day 4, because there are no other decisions after that. The driver goes from location A to C on day 4. I'm also going to let it go into the sync node. Likewise, if a driver goes from location B to A on day 4, he's going to go into the sync node. B to B on day 4, going to the sync node. B to C on day 4, also going to the sync node. Driver going from C to A on day 4, still going to the sync node. Driver going from C to B on day 4, still going to the sync node. And the driver going from C to C on day 4, still going to the sync node. So all of the flows originating on day 4, they're all going to this trash can, essentially. It's a dumpster. Because after day 4, I'm not making any other decisions. Likewise, likewise, likewise. If a person is sitting idle in location I, in location A day 4, he's going into the sync node. If a person is sitting idle in location B on day 4, he's going to the sync node. And if a person is sitting idle in location C on day 4, he's also going to the sync node. Okay, so all the flows that are originating from different nodes on day 4, they're going to this dumpster bin. Okay, good. So now let's look at a full network flow problem that takes place on this type of network that we just drew on this top page. And let's look at one of these nodes, and let's look at the flow balance constraint for one of these nodes. Let me take this node. Location C on day 1, location CD on day 1. Let's write the flow balance constraint for this location, this node. the node corresponds to location C on day one. Let's write the flow balance constraint for this node, which corresponds to location C on day one. What is that flow balance constraint going to say? What is the total flow out of this node? XCA. Let's write it in red. XCA1 plus XCB1 plus XCC1 plus ZC1. This is the total flow out of this node, node C on day one. XCA1, XCB1, XCC1 plus ZC1. There is no inflow. That should be equal to the availability at this node, which is SC. Okay. In other words, this constraint is equivalent to XCA, XCB, XCC, XCA1, XCB1, XCC1, XCA1, XCB1, XCC1 plus ZC1 is equal to SC. So this constraint is of the form XCJ1 add over all J plus ZC1 is equal to SC. Is that constraint? Okay. This constraint exactly has this form. Here we write this constraint for a general location I, but if you specialize this constraint for the location C, XCJ1 added over all J, XCJ1 added over all J plus ZC1 is equal to SC. Okay, so then these constraints that we wrote in our formulation are giving us the flow balance constraints for the nodes at the beginning of this network. So what else? Let's take a node. Let's take this node corresponding to location B in day 3. Let's take this node corresponding to location B on day 3. Let's look at what the flow balance constraint for that node is going to be. We're going to write a constraint that says total flow out of this node should be equal to total flow into this node. What is the total flow out of this node? XBA3, XBB3, XBC3. XBA3, XBB3, XBC3 plus ZB3. This is the total flow out of this node. This total flow out of this node. XBA3, XBB3, XBC3 plus ZB3. This is that red arrow. Okay. So this is the total flow out of this node. What is the total flow into this node? What is the total flow into this node? XAB2, XBB2, XCB2. XAB2, XBB2 plus XCB2. What else? Also ZB2. This is the total flow into this node. Okay. So for this node in the middle, for location B on day 3, we wrote a flow balance constraint that says total flow out equals total flow in. Let's look at this constraint. XBA3, XBB3, XBC3 plus ZB3. So that's XBA3, XBB3, XBC3. So that constraint is of the form. X, BA3, BB3, BC3. So I'm adding X, BJ3, and overall J, plus ZB3 is equal to XAB2, XBB2, XCB2. XAB2, XBB2, XCB2. So this the right-hand side of this constraint is of the form XJB2 and overall J plus CB2. Good. So then the flow balance constraint for the intermediate node B over here that we wrote has this form. Let's say again, this is our formulation that we came up with. So let's look at these constraints. Specialize these constraints for the location I equals B and for time period T is equal to 3. So then XBJ3 added over all J, XBJ3 added over all J plus ZB3 equals XJB2 added over all J plus ZB2. Okay, so then in our formulation, these constraints that we wrote corresponds to the flow balance constraint for the intermediate locations in the intermediate days. Okay. So then in the formulation that we wrote, these constraints correspond to the flow balance constraints for the nodes at the beginning of our network. And these constraints correspond to the flow balance constraints in the intermediate nodes. So then this formulation that we have is nothing more than a network flow problem that's taking place over this kind of a network. And these networks are called state time networks. So as we go this way, time goes forward. And as we go this way, these are the different states of our drivers. He could be in state, driver could be in location A, driver could be on location B, driver could be in location C. These are the different states of our drivers, and this is the different times. So these kinds of networks are referred to as state time networks. So whenever you're speaking the jargon with a person who does optimization, if you just tell him, or if you just tell her, look, I formulated the problem over a state time network, then they'll immediately get what kind of a formulation that you're dealing with. Okay, so this is kind of a nice interpretation of the formulation that we wrote. So our formulation of the dynamic driver assignment problem is essentially a network flow problem. These constraints are the flow balance constraints for the nodes at the beginning of our network. And these constraints are the flow balance constraints for the nodes corresponding to the intermediate nodes. Good. So this is a good point to stop. In the next lecture, we're going to look at one more integer programming formulation for a logistics-inspired problem, and that is going to be the traveling salesman problem. So let me stop my share. So today we looked at integer programming formulations of capacitated and uncapacitated facility location problems. And also we looked at an integer programming formulation for this dynamic driver assignment problem. And the cool thing about this dynamic driver assignment problem was this state time network idea. Another important thing about this dynamic driver assignment problem is that the decisions that I make on day t-1 affect what decisions that I can make for day t. So our decisions on different days are linked to each other. Those are important modeling concepts to see, the important modeling concepts to understand. Again, this state time network idea is also a cool idea. It's kind of nice to know the jargon. Whenever you talk to somebody, hey, I formulate this problem in a state time network, he or she's immediately going to understand what you're talking about. When we come back in the next lecture, we're going to look at one last third logistics-inspired integer programming formulation, and that is going to be the traveling salesman problem. Good, let's stop here.